Chairman of Pragya Foundation, welcoming you all for today's talk of the week, Pragya Prerna. The speaker of the day is Dr. Krupad Murthy, Professor of Physics from Roosevelt University, USA. He is with us for today's talk on Classics 2, Quantum, and it will be an interactive session on behalf of Foundation, Pragya Foundation, on behalf of my entire team, student community, faculties, and viewers. Sir, I welcome you, sir.
Welcome. Thank you so much.
Before we go to the interactive session, it's my honor, my privilege to introduce Dr. Krupad Murthy for you all. Professor Krupad Murthy is an accomplished educator and scholar with over 30 years of experience teaching physics, mathematics, business statistics, and data analytics. He has served in significant academic roles at leading US institutions, including the University of Phoenix, Roosevelt University, Oakland Community College, and DePaul University. At the University of Phoenix School of Business, he held long-term appointments beginning in 2004 and served as Content Area Chair and lead faculty member from 2009 to 2015. His work emphasizes statistical analysis, business stimulation, data mining, and the integration of real-time analytical models into business and STEM education. Across his career, Professor Murthy has taught graduate and undergraduate courses in business statistics, managerial decision making, research methods, physics, and mathematics, while contributing to curriculum design, faculty development, and academic policy initiatives. So, of course, in this interaction session, we are going to take questions on these aspects. He has also engaged in applied research as an epidemiology data support analyst at Pennsylvania State University, employing predictive analytics, statistical modeling, and epidemiological methods using SAS, SPSS, and advanced analytical tools. His research has appeared in the Journal of Dairy Science and international conferences. He holds multiple master's degrees in electrical engineering, physics, and engineering physics, and has received the Faculty of the Year award in 2009. Sir, I welcome you again and over to you for the talk on classics to quant.
Thank you, Arvind. Really appreciate it. And so, my topic of discussion today would be on classical to quantum, how classical physics or classical mechanics has transformation to quantum mechanics. When you look at classical mechanics, we go back to the Newtonian mechanics, which is on a macroscopic scale. Like the best example, if you throw a tennis ball, you can predict at what velocity you're throwing and how far does it go and what's the range. You can actually predict in the classical or the Newtonian mechanics. And the classical or the Newtonian mechanics can only apply up to the Maxwell's equation like optics, thermodynamics, but beyond Maxwell equations, the classical mechanics will not be applicable because we are approaching the quantum, which is the speed of light. So the classical mechanics holds very well, at the basic to estimate the velocity, the kinematic equations, and thermodynamic equation, even the optics, all of them works beautifully in classical or the Newtonian mechanics. But when we switch or when we talk about approaching the speed of light, that's where the classical mechanics may not hold very well. So that's where we talk about the space-time, like the Einstein space-time duality, and we slowly move closer to the speed of light. Nobody could approach the speed of light. We can go close to the speed of light, like 0.99 c, but that's when the quantum mechanics comes into the picture. A couple other things. Next time when I meet in person, face to face, I can show you more slides, explain why the classical mechanics fades away or fails, and then we move on to the quantum mechanics. Uh, when we talk about the Maxwell's equations, that's the combination of electric field and the magnetic field. Then when we combine those two, that becomes the speed of light. And the speed of light is like 186,000 miles per second. That's when we have to switch to the quantum mechanical model. So a lot of quantum mechanics is applied even today, like quantum physics to artificial intelligence, robotics, many other applications we can discuss more in detail. Uh, in classical mechanics, you can predict exactly on a macroscopic scale, as I said before. And in quantum mechanics, it's a probability. What's the probability that something is between the two walls? When you look at a quantum well, a particle in a box, you don't know where the particle is, what the wave function is. I know I'm extending a little bit of the wave function, but you can never predict where the particle is and what's the velocity, what's the momentum in a quantum well. So there's a lot of unpredictability in the quantum approach. One other thing I need to mention that quantum mechanics can be applied even at a closer to the speed of light. When Einstein came out with, as most of you know, E equal to mc squared, m is the mass and c is the speed of light, and E is the energy. So that's where the quantum mechanics slowly start building up. Give me 1 second, I can exactly talk about, yeah, that's fine. So when did the quantum mechanics begin or the quantum physics began? So light can be treated as a particle, or light can be treated as a wave. In classical mechanics, light travels straight line, particularly in straight line at the speed of light. But in the quantum mechanics, light has a duality. It can travel in the form of particle or it can travel in the form of wave. When I say light as a particle, we call light is made up of photons, small particles, which has some energy. Energy is given by simple mathematical model, some constant, which is called the Planck's constant, times the frequency. And so light you can treat as a photon, which has some energy. And light can also travel in the form of a sine wave or a wave. So in Michelson-Morley experiment in quantum physics, that's the first thing we do it in to figure out how does the light travels in the form of a wave. So there is a double slit experiment which is called the Michelson-Morley experiment, which is the earlier experiment what Michelson did, where light can not travel in straight line, it could travel in the form of wave, constructing two types of interference, constructive and destructive interference. When two waves meet at the same point, then you get a bright spot or a bright fringe, they call it bright fringe. When two waves are out of sync with 180 degrees out of phase, then you get a dark fringe or a dark spot. That's where we think light can not only travel in straight line, it can travel in form of wave. That's the quantum optical approach. So when we talk about quantum mechanics, there's many other fields even in quantum field like quantum gravity, quantum optics, quantum electrodynamics. and that's a huge subject by itself. Also, I want to mention here there is what is known as a grand unification of theory. There are four fundamental forces in nature. One, of course, most of you know the gravity, the G force, and then there is the electromagnetic force. It's a combination of electric force and magnetic force. Then the next we talk about is the nuclear force. Just to mention the nuclear force, whatever happening on the surface of the sun, it's a combination of hydrogen and helium. It keeps burning fossil fuel, and that's actually called a quantum phenomena as well. And one other example I can even look at as even light. Light, as I said before, it has a duality. Duality means it can travel in the form of straight line, carrying out the energy Planck's constant times the frequency of the light, which is the photon energy. And light can also travel in the form of a sine wave. And we can talk about all that in the next coming topic of discussion. So going back to this fundamental force of nature, so nuclear force is it can be looked at as burning of fossil fuel. The good example is the sun. Sun keeps burning with hydrogen and helium. That's nothing but a nuclear fusion process, you know. And it's though the surface temperature of the sun is 6,000 degrees Celsius, there's a lot of hydrogen is a positively charged, helium is a positively charged, and they keep fusing and it keeps burning energy. And that's actually, it's nothing but a quantum phenomena that's happening in our day-to-day life. The next is the electromagnetic force. When we look at motors, when we look at coils, when we look at a doorbell, so there's nothing but a combination of electric force and a magnetic force. But if you combine electric force and magnetic force at the Maxwell's equation, the four fundamental equations of Maxwell's, they talk about the magnetic field, they talk about the electric field, the E force. That when you combine those two forces, that carries the energy, which is the speed of light, which is 186,000 miles per second. In the metric system, it is 3 times 10 to the 8 meters per second. Okay, and that's we can talk about in quantum optics in more detail. And there is also a quantum gravity, as I just mentioned before. Quantum gravity is nothing but gravitational waves. And if you look at the galaxies, when the galaxies collide, when the galaxies interact, or when the galaxies are separated by far distance, those are the combination. Way it's holding up the galaxies are the gravitational waves, quantum gravitational waves. So we know gravity is 9.8 meters per second squared. That's the basic, we know that's a classical perspective or classical physics perspective. When you look at a quantum, we talk about quantum gravitational waves. That's when we talk about black holes, neutron star, collapsing the star, and the light will not escape, from a black hole. What else can we talk about on quantum? There's tons of application on quantum physics. Yeah, when you look at even in a quantum well, particle in a box, we talk about many of the models, one of the Schrodinger wave equation model, and that's when a powerful mathematical model to figure out whether how much energy a particle and an atom between the two walls. And there's also a couple other models like Heisenberg uncertainty principle. And you can never measure the distance, the delta x, or you can never measure the delta p, what is known as the momentum at the same time. And that's defined by some Planck's constant, which is generally most of you know in quantum mechanics, delta x times delta p is approximately equal to some constant, which is known as the Planck's constant, which is a very, very small magnitude, 10 to the minus 34 joules second. I know I'm bringing a lot of this concept, but unless we look at this in real time, then only we can explain it far more in detail. Do you have any other
Yes.
questions so that I can interact
Yeah,
even more?
sure, sir.
This is basically the basic introduction of what a classical physics and how we transformation into the quantum mechanics. Just because quantum mechanics, you're looking at a higher speed of light model. When something velocity v approaches the speed of light, it doesn't have to be equal to the speed of light. In calculus, we call it something is approaching, same thing, v approaching to the speed of light. Yeah, we'll get to that quantum mechanical model further down the line.
Sure, sir.
Yeah.
Sir, I have
Sure.
few questions raised by the viewers as well as from my colleagues.
Sure.
I'll be putting the questions before you. Kindly permit me, sir.
No problem.
Okay, sir. With respect to curriculum design, here are a few thought-provoking questions like how can modern physics concepts, especially quantum theory, be integrated into undergraduate curricula without overwhelming foundational learning outcomes?
I would say, in any subject you thought you have to be teaching, I would strongly recommend you need to explain the concept, that's for sure, but also at the end of the putting all the concept, you need to make sure where this concept is applied in real time. Let me take you back to the one basic example, like a simple pendulum, right? In classical physics. Yeah, we know the simple pendulum, and where do we follow that simple pendulum? All the mathematical, the period, the length of the pendulum, the gravity, like T equals to 2 pi square root L divided by T, all that many of you know from basic high school to college physics. That's fine. All that mathematics, all that how to design the pendulum, given the length and what's the period. But where do we apply? That's the key thing, we need to be teaching in the classroom. So the best example of a simple pendulum is a clock pendulum, or sometimes they call it grandfather's clock pendulum. You probably see in most of the homes, and that's where you can transformation into from a mathematical model, what you learned in the classroom, into the real time in any clock pendulum you see on a big wall, whether it's in a big hotel or whether it's in nice colonial homes. And here's another example of how we can interpret the momentum. What is momentum in classical physics? It's simple, like mass times the velocity, right? Where do we, yes, you can work out all the problems, but if you play a tennis ball and if you play cricket, so you got a mass of tennis ball, and if you hit with the velocity with a cricket bat or a tennis racket, you carry a momentum. Momentum is kind of, you could say, the energy, it's mass times the velocity. So if you take a half a kilogram or whatever, the mass of the tennis ball times the speed at which you're going to hit the tennis ball, whether it's through the cricket bat or the tennis racket, it carries a lot of momentum, it carries a lot of energy. The bottom line, what I'm trying to say is you need to explain where the momentum is applied in real time. Same thing, you look at, there's tons of examples, like thermodynamics. Thermodynamics is like an abstract concept. We talk about what is known as the Carnot cycle. And one of the best example, Carnot cycle, Carnot diagram, let me put it simply. It's a very abstract concept. Where do we use that Carnot cycle? The refrigerator. Everyone has a refrigerator, and the efficiency of a Carnot cycle is less than 1. It's probably 0.9%, which means 90% efficient. Any fridge in any given home is only 90% efficient. It's not 100% working because you lose so much heat. Whenever you open the fridge, you lose so much heat. To regain the coolness of the fridge, it needs to work harder. The coil needs to cool, the cooling coil needs to cool up. The bottom line is the Carnot cycle, you can relate to the fridge in everybody's home. The bottom, once again, to sum it up, any concept you teach in classroom need to be explained with a real-time example. That's the best way the students can grasp the concept they can relate what they learned in the classroom into the real time.
Sure, sir. Um, what strategies can institutions use to balance classical physics content with emerging interdisciplinary topics like data science and analytics?
Classical physics.
Yes.
Classical physics and data science is two different subjects. That's why I need to ask you the question. Classical physics is more like a Newtonian physics, and data science is collecting the data, analyzing the data. Like when you look at healthcare, for instance, if you want to estimate is the drug effective, whether it's insulin is effective for, let's say, pharmaceutical industry is going to come out with a new medication. Is the drug effective? Whether it's what do you call it? There's many drugs I can't think of, like metamorphin and many other insulin drugs like Farxiga. That's right, Farxiga. Farxiga is an insulin, and that brings down the sugar level. But to find out whether Farxiga is a good medication for the community or for people to use, you need to study a sample. You need to collect a large amount of sample, make sure you're going to test the sample again and again. You need to do repeated and random sampling to make sure the drug is effective or not. So that's what a data analytics is. I don't know how I can relate the classical physics to the data science. They're both two different concepts. Classical physics is learning the concept where you can apply in engineering, math, medicine, optics, thermodynamics, or even in mechanical engineering. But data science is a little bit away from.
Agrees. This is a general question. How should curricula evolve to better prepare students for rapidly changing scientific and technological landscapes?
Scientific and what's the last one? I'm sorry.
Technological landscape.
Sure. Yeah. So when you look at the curriculum development, that curriculum is like the lesson plans or what you teach for the semester that need to get updated. What is going on in the industry? What is going on in real time? We need to bring back those examples and put that in the curriculum. You cannot teach the old physics, you cannot teach the old chemistry. That's not the way the classroom should be set up. In the United States, we change the curriculum so often. So often means, what is going on in the industry, we need to bring back those concepts, put that in the curriculum, teach it more effectively. The students are prepared for, the job market or even for any type of engineering or even in biomedical as well. So curriculum need to be updated so often. That's why we have curriculum board. We meet once every summer. Yeah, usually we meet June to August. So that curriculum need to be updated constantly because the technology is changing. You cannot teach the old chemistry, old biology. That gets obsolete. We should move with what is going on with.
Yes, sir. I think even for teachers also.
Oh yes.
There is a need for them to update their knowledge.
Absolutely.
With respect to their subject.
Right.
They have to go out of the syllabus.
Right.
They should not simply stick on to the syllabus. The
Right.
syllabus, it's just for evaluation purpose, they have given something. They have to go out of it,
Right.
update their knowledge and
Right.
further update the same for the students.
Correct. Even I don't think they should have any exams, Usually you have 4 exams, like a midterm and a final. Way I do the classes, whether in data analytics, whether in microeconomics, I've taught many classes. You got to put these students into real-time perspective. Just have one exam, that's it. The rest should all be project. They need to bring their own expertise, what they learned in classroom, and they need to apply whether they can go to companies, get the data, and they need to analyze. So that's the only way students get not only the real-time example, what is going on in the industry or what is going on in this corporation. You cannot have 3 exams, quizzes, homework. Yes, it's good, but that need to be limited to 30% of the grade. The rest 70% should be all real-time learning.
The next question is relevant to what you said. So, what role should experiential and project based learning play in science and engineering curriculum design today?
Yeah, as I said
Yeah,
before, as I said,
yeah,
same
yeah,
thing,
I said,
yeah, as I've already
yeah, yeah,
mentioned,
they have mentioned.
real time is the best way to learn. Yeah.
How can academic programs ensure that curriculum updates remain aligned with industry expectations and research advancements?
Yeah, as I've been saying again and
Yes,
again,
yes,
you
yes.
need to bring the speakers from the corporation. That's what I do. I bring many in my classroom. I've taught physics, I've taught high energy physics, I've taught engineering physics, I've taught even data analysis. I bring from people from corporation, not the alumni. Alumni, like the students who have graduated, they're willing to come. Dr. Murthy, I would like to come and help you. I give them an opportunity, and I've invited many guest speakers. And as part of classroom learning, I don't teach that day. They learn so much. The students learn so much out of from these experiences. That's the best way to learn. You cannot teach the same thing again and again. I don't do that. I don't use the textbook at all in my classroom. I never ever use the textbook. Yeah, they prescribe the textbook. That's not the best way to learn. You know. And I looked at the concept, what I should be teaching, bring in real-time examples, and do this. I've been That's the reason I've been getting so many Faculty of the Year award. What happened in 2009, I was one of the esteemed faculty member of 2009. And I've got so many awards, I don't put them on my thing, but the recognition is fine. But at the end of the day, the student need to gain the knowledge. Even today, after 20 years, and my students come back and tell me, Dr. Murthy, what you taught me, I got this job, that makes me
Yeah,
very
that's the
satisfied.
real award.
Yeah, that makes me really proud,
Yeah, that's our achievement.
Exactly. I got students from like Brazil, like Veronica, many students. Glad to, I'm
Yeah.
still in
And
touch.
we will also be happy that the purpose is served,
Yeah.
what knowledge transformation has occurred
Right.
in the right way.
Oh, yes.
So with respect to faculty development here, there are a few questions like what types of faculty development initiatives are most effective in helping educators teach complex subjects such as quantum physics?
Yeah, quantum physics, the bottom line, you got to be good in math. Good in math, I've had engineering physics. You got to take Laplace transformation, you got Fourier transformation, you got to take Bessel function. It's a high intense math. Math, if you know math, you can do physics, you can do engineering, you can do electrical engineering. Even yesterday, I was at the Indian Institute of Science, and I was talking to a few professors. When we look at the quantum computing, yeah, people talk about AI and all that. It's easy to talk about. There's so much math behind it. You talk about metrics, tensors. What's the other word? Metrics, tensors, and there's a new mathematical model. But anyway, vectors, fine. Vectors is good. Metrics, the tensors gets even more complicated. These are all extremely high level math. It's extremely difficult, and you got to have a good math background. If you got a good math background, then you can handle not just physics. You can have biomedical engineering, even like classes like medical physics. I've taught two medical physics classes a few years ago on radiation physics. You need a lot of math to understand what that radiation physics is. Yeah. And even with AI, it's not the hardware. And like yesterday, we were talking with a few professors, and we were talking about how when you build this AI machine, it generates a lot of heat, thermal heat. You need to cool the system. The only way you need to cool the system, we need liquid helium-3, which is a isotope which is so expensive on the surface of the Earth, and you got to take it to Moon. Moon has a plenty of helium-3 because the gravity is low, 1.6 there. Here we got 9.8. Anyway, it gets into a lot more complex, but as I said again, the math is a fundamental.
Yes.
Whether you take chemistry, biology, physics, without math,
Yeah.
nothing can be accomplished.
Sir, how can institutions support faculty in adopting innovative pedagogical tools like simulations, digital labs, AI-based learning aids, and so on.
Could you repeat that question again?
So, how can institutions support
Ah.
the faculty?
Okay. The institution should be supporting all the time because institutions should be responsible equally to bring in this corporate expertise and so that these teachers, the management, everyone should be aware what is going on in real time in big corporation. Like I have brought guest speakers from Boeing, I brought guest speakers from Abbott Pharmaceuticals, I brought from Pfizer, uh, and I brought one student who worked for a startup software company, and they were so good. They actually teach us more, and even as a teacher, I learned so much from them. And even the students are very smart sometimes, and I have had some few students, and we learn from them as well. It's not always the teachers are the best. That's no longer that's a myth, but we learn from the students as well. It's an interactive learning. But the best way is to learn, bring in the expertise from the corporate, and so that the teachers, the management should be aware, and they should be constantly updating their curriculum. That's the only way you keep up with what is going on in the real time.
Sure. Uh, Sir, what strategies can be used to build faculty capability in mentoring students for research and scientific inquiry?
First of all, you need funding. Research, without funding, nothing can be, That's one thing I found out yesterday. I was talking at the Indian Institute of Science. We had a long meeting with few faculty members. It's amazing, They got good amount of funding, and sometimes they also strive for more funding. And one student who did on quantum computing, and there's a lot of error rate going on. Anyway, he graduated last July with a PhD in nanoscience, and he moved to Paris. And he's a phenomenal student. He's an extremely bright student. I was talking to um, Dr. Dr. Shiv Shankar and few other professors. We had a good discussion about 7, 8 faculty members. It's amazing, these students really strive so hard, and yeah.
Sir, what mechanisms can help faculty remain current with interdisciplinary fields such as physics, analytics, education?
It's not physics. It could be engineering. It could be biology, biomedical. Just keep updating. Just keep updating the knowledge. Read the updated research publications. Don't read the textbook. Yeah, textbook. They should have mastered after 10 years of teaching. They know what they should be teaching. These teachers, these faculty members should be on top of the research publication. Look at the journal, look at what is going on, and they bring that expertise into the classroom. And at the same time, they got to be changing the curriculum as well, constantly. You don't need to change the whole curriculum all month. You can change here and there, keep on updating. Yeah, that's the best way for the student learning, and that's the good way to keep up with the academic program, and as well as for the, good academic achievement from the school perspective as well.
Yes, that's the thing. Unfortunately, the teachers restrict to their subjects.
Yeah.
So they have to go beyond that. Whatever, if they have done some research in some field, how can it be extended to other fields, other areas? If it is in a physical science, why not that be in a life science field? So they are not thinking on those lines as well. That's not reaching the students also. That's a very unfortunate thing, sir. Uh, how can institutions encourage more collaborative teaching or co-teaching models across departments?
I think that's totally the management issue, Yeah, management need to work with the faculty members and the board members, I don't think faculty members have I should say, no responsibility. At least they should provide or feedback to the management, and management should be on top. That's the only way you keep up the esteem or the respect or, academic standards for the school.
So don't you think the management has to insist for it? They have to do.
Yeah. I don't know, I'm not, I shouldn't mention this. Here back in US, same thing in Europe, management listens. They listens what the faculty members say. It's a good transparency. Here I don't see any transparency in some of the schools. That's unfortunate. That need to be changed. Like schools like Indian Institute of Science is amazing, I tell you.
Yes.
They listen to the faculty members, they get good funding, such high amount of research going on in nanoscience. It's amazing to see. I'm so proud what they do. But apart from IIC, from some of the local colleges, I think they need to be much more transparent and much more listen to the faculty members. That's the only way they can succeed. Otherwise, I know I should not bring those issues during this
Got
type
it,
of
sir.
conversation,
Yeah,
but
yeah. Got it.
that's the way it is.
Okay, sir. So with respect to academic policy initiatives, strategic questions are there. Let me take up that. What academic policies are necessary to support the integration of interdisciplinary programs in higher education?
I mean, interdisciplinary, every department need to collaborate. Like if you got chemistry or physics or biology, they need to bring the two departments together, work on like biomedical or biochemistry project, Then only you can interface the faculty members. And when you say Department of Biology, they just cannot isolate themselves from Department of Chemistry.
Yes.
They all need to collaborate and bring students to work on biochemistry or biophysics or medical, any. So these faculty members need to collaborate. There should not be any, they should never set boundaries.
Yes.
They need to collaborate among themselves to come out with nicer project and work with the industry. They need to work constantly with the industries, local industries. They need to put their efforts in, that's the only way you succeed from the student perspective. Student will learn, they will recognize their talent and they will move on. Yeah. And one day they will come back and they will even support the school in one way or the other.
Yes. Sir, how can institutions revise assessment policies to better reflect conceptual understanding rather than role learning?
Yeah, as I said earlier, the best way is to learn is don't give too many exams to the student. Don't give too many assignments, Yes, give 30% as their assignment. The rest 40%, they should be working on their own project. That should be 2 projects, which is like the rest, whatever that 60%. 60% should be project-based, real time. They need to go to a corporate or they need to work on it. They need to look at research publications and then they need to come up with their own creative learning, creative strategy so that what they can bring into the classroom, what they learned in the classroom plus what they learned in the project, they should be doing a presentation at the end of the semester or at the end of their academic program. Yeah. That's the best way. That's exactly what's happening in US schools.
Oh, sir, what policy frameworks can facilitate continuous curriculum revision to keep pace with scientific advances?
Yeah, management need to listen to the faculty members and faculty, it's all, what the team effort. Without the team effort, the school cannot progress, school cannot succeed. The management need to listen to the faculty members and bring some this at the same time, bring from the corporate, whether it's a pharmaceuticals, whether from companies like local companies, and listen to what they're doing. So they need to bring in, or they need to have some from the corporate or the board member, and so that all can listen to each other, update their curriculum, and then this is all for student success. The bottom line, at the end of the day, student need to succeed. Yes, faculty needs their paycheck, faculty needs their money, But at the end of the day, it's what you look in the students' academic success.
Why, sir, it's my question.
Hmm.
Why there is a need for us to collaborate with or join with the corporate world for everything? What's the need for it, purpose for it?
Because whatever happening, outside, that's what's happening in corporate. Yeah, you can take physics or chemistry or biology. Yeah, you learn from the textbook, right? That's it. You cannot use a textbook into the real time. Let's say a student who graduated with bachelor's or master's in biology, he cannot work in an industry right away because he has learned from the textbook. He doesn't know what is going on in the industry. That's why, either they need to get an internship or bring from an industry, and they need to collaborate, and they will tell you these are the things we're doing, and if you're gonna work for us, you should have these biological concept, you should have this, chemistry or biochemistry concept. Then only you can belong in my, industry or belong in my corporation. So definitely a corporate interfacing is a big asset for a lot of schools. So we have seen in US schools, that's exactly, I've seen in US all the time. As soon as you finish 2 semesters, fall and spring, they get a summer internship. They learn so much, and before they graduate, they will have plenty of job offers. That's exactly what, Indian schools should be doing the same. I know it's tough, but somehow that needs to be the focal point, you know, for the students to find a job easier way to do internship. They don't need to get paid. At least they can work free. I've worked free at the Indian Institute of Science, learned a lot.
Sir, how can academic policies encourage cross-institutional collaboration, international partnerships, and research exchange?
I've already
Yes,
mentioned.
yes, yes.
Uh,
Sir, what governance structures best support innovation in teaching, learning, and educational technology adoption?
yeah, innovation, like many students are very smart and nice, good. So the only way they can be innovative, they can do creative ideas, creative research, is to work on their project. Yeah, teach the basic concept and let the student think about what else they can do based on what they learned in the classroom, whether it's thermodynamics, whether it's biochemistry. They can always come out with a nicer project. Either they can work on their own, or they can look at the research publications, they work through an industry and come out with their own innovative idea. That not only helps the student to think better, and it's good for the classroom, and it's good for the industry as well.
Here is a question from viewers. How can physics education uh, leverage data analytics to help students better interpret experiment simulations and real world data sets? I think as per you, more than physics, maths is required.
Well, what was the last one? Work physics?
Experiments for better interpretation of experiment simulations and real world data sets.
I tell you, whether you take biology or chemistry, let me tell you one thing. Uh, Two things I need to say. You're going to be applying the concept, whether you learn chemistry like an organic molecule or organic structure for benzene or something, and where can I use this model, or some, I know many things I can think in chemistry or even in biology, DNA or even in physics, like the one good example I can think in physics is optics. Yeah, optics. Yeah, optics is a good example. Where we use optics? Yes, we learn, concave lens, convex lens, photometry. Where do we use in optometry? Whether you use a diverging lens, whether you use a converging lens, what's the focal length and all that. Yeah, anybody could read off a Google website or a textbook, but where do you use it? That makes it more meaningful. And don't physics or chemistry or biology, you need to be applying to some engineering physics or biochemistry or biomedical. Then only it becomes more meaningful. Just take the basic courses will not, you need to start applying into engineering arena.
Correct. Sir, what should an ideal learning pathway look like for students aspiring to combine physics with business analytics or data science?
That's two different things.
Yeah.
Physics or chemistry or biology is something, data analytics is big data. That's they call predictive modeling, data analytics. I've done for work for Penn State. Uh, we did publication in Journal of Dairy Science, and I spent one summer in actually in cattle farms to make sure that these cattle farms do not get any infection. We treated them with antibiotics. We worked from mornings till 6, evening 6 o'clock. During summertime, 3 months, we collected a lot, plenty of data, thousands and thousands of data. I worked with Department of Veterinary Science. And so data analytics is collecting the data, what the data is, and you're gonna analyze and you're gonna inference, you're gonna see what the data means to you, whether that antibiotic is helpful for the cattle farms. So data analytics is a separate field, physics has nothing to do with that.
Uh, Sir, how can institutions incorporate analytics driven decision making tools into STEM curriculum planning and assessment?
Yeah, STEM is, I don't know how much STEM is implemented here, science, technology, engineering, and math. But I would say everyone to take math for sure. There is, people talk about quantum, AI. It's not what you say. AI has not even picked up yet. AI will pick up by 2030. Definitely, you will start seeing AI in medicine. You know, but to learn AI, there's so much math goes behind it. I was again, I walked into the IAC library, I looked at few books on quantum computing, and I was amazed to see so much matrix algebra, tensor algebra, so much math goes behind it. So STEM means, yeah, science good, but math is the essential for any, whether you go into medicine, you got to have some basic calculus. Like I'm not saying triple integral calculus. At least a single or a double integral would be a big differentiation. Of course, would be a big help. Yeah.
Sir, how can analytics help identifying students' learning patterns to personalize instruction in complex subjects like quantum physics?
See, analytical doesn't come in quantum physics. Quantum physics is a different field. You're talking about AI, and you're talking about quantum optics, quantum gravitational waves, and I don't think analytical is something you collect the data, you do some kind of a predicting modeling. I don't think quantum physics uses a whole lot of analytical tools, at least to my knowledge.
Are we not applying any of the principles or some laws like of quantum physics to analytics?
Yeah, I think no, no. I think AI, the beginning of I should say, AI, the fundamental of AI is basically goes back to quantum physics, quantum well. Without quantum well, like making of diodes, transistors, computers, so on and so forth. Now we are talking about, quantum modeling, quantum computing, AI. It all began from physics. Many would not understand what it is. Quantum physics is a fundamental building block. Of course, math, quantum physics, and math, that's the building block where AI is. Without quantum physics, I think they won a Nobel Prize last year for AI. If you look at their recent publications, their background is all about quantum physics. You know, yeah, physics by itself could be dry, chemistry by itself could be dry, but when you look at a quantum level, quantum physics, they've taken up to this for AI. And AI artificial has not even picked up yet. People talk about it, and by 2030, US is going to pour billions and billions of dollars into AI. You will start seeing, especially in medicine and pharmaceutical industry. Yes.
Yes, sir. Thank you so much for clarifying all our doubts or answering our questions from the viewers and my colleagues who were had asked. Uh, I like to mention one thing. Though today the title of the talk was given as classical to quantum, Sir has just mentioned the elementary aspect, and he will be taking going to the depth of the subject in our next session or the next talk. Uh, so you have to wait for it. That will be brought to your notice. So we will conclude this session with this. Sir, anything from your side to say to the viewers?
Nothing much. Thank you for giving me an opportunity. I really appreciate and good questions, and that's all I could say.
Yes. On behalf of all the viewers, on my own behalf, and on behalf of the Pragnya team and Therapion who have collaborated for this session, to run this session, thank you so much, sir. Our humble pranams to you.
Thank you.
So for giving your time, coming all the way to Pragnya Foundation and sharing your knowledge, and I hope this is never a waste of time. It will be this time will be much useful for the students also, as well for the faculties to design in with respect to it can be for evaluation, it can be for curriculum designing, and so on and so forth. So thank you so much.
You're welcome. Thank you so much. Bye bye.
I didn't want to go. You have to end the session.